So hello, I see that we have 2 people online. Hopefully more will join. So while we are waiting for the people to join, please, okay, I see already 4 people. So please could you type in the chat who we are here. So say hello in chat. So I know which people are here today. And then we'll start with the task, and it's going to be session going to be like about 1.5 hours, so it's not going to be too long today, but we'll cover quite significant topic, and the homework also will be I think interesting, challenging, significant, and stuff like that. So yeah, I see Lee, Christopher's, okay, that's great. What about others? Okay, great. Also, Kirilo, excellent. So hopefully others will look up this later, because there are some other students who are doing the research work with me, and this is quite mandatory that you follow these things, otherwise it will be quite difficult. So let us see what we have here. So what about, okay, so hopefully delay will not be too big. Hopefully delay will not be too big. So yeah, just a second, I will start in a second. So from the people who are here, at least 2 of you already have, okay, batch normalization. So it's not really, batch normalization is not around the 0 to 1, but around the standard deviation. It's, you could imagine it's something like -1 to 1. But okay, I will briefly touch the batch normalization and normalization techniques at the end of our today's session, because the homework will be kind of, I will give you the state-of-the-art type of the architecture for autoencoders. So it will not be like totally state-of-the-art, but yeah, okay, we have used and not understood. So yeah, it is, as you understand, normalization. So you want to place the features around the 0. So, and the batch normalization is kind of tries to estimate the feature space along the whole data set based on the batches. So it's not optimal. And that's why, as I say, I will touch that into like that at the end of this session. So the first slide, this is regarding the autoencoders. Autoencoders do not require labels. So the autoencoders work without labels. You don't need to know what are the labels, you know, like we have supervised learning, the middle part, the icing of the cake. So this illustration is made by LeCun, who is one of the most important researchers in deep learning. So he was the one who invented the LSTMs. He was really influential. Also, so I'm not sure about LSTMs, but the convolutions was his part. He also worked a lot with energy models, a lot with the embedding models. So he gave this illustration that the icing, like in a cake, icing, the chocolate part, that is supervised learning, where you have the labels. Then the reinforcement learning, that I'm not sure, like, so there's at least one girl that is doing the research with me that should work with that. So that is like the policy of how to play games and the policy how to make decisions. So that is really, really complicated and actually very small part of the deep learning. And then the huge part of the deep learning that is in the middle part of the cake, like the bread itself, is unsupervised learning. So that is like when the kid is looking at events in the world, and the children is learning from them automatically without any labeling. So this is one kind of model that we will touch today. So let me introduce to the autoencoders. So I will make the next slide as well. And if you have questions regarding this part, then also please type in the chat. So the autoencoders in a very primitive manner looks like something like this. So they are the encoders. So encoders we already know how to make. We already know how to make dense nets, res nets, all sorts of stuff. So far we have done this part till the bottleneck Z vector, latent space vector. So that is the idea that we can encode high-dimensional image into low-dimensional, 10-dimensional probability distribution that we can classify. But we could also compress this high-dimensional image to something like 32-dimensional latent vector, for example, or 3-dimensional or whatever. And then we can deconstruct the whole image just using the small representation and create something like this. So the decoder part. Decoder part is based on transposed convolutions, or there are more modern approaches. At the end, like in the homework, I will give you modern approach how to do this by NVIDIA, but like nobody actually use in modern models transposed convolutions. They have checkered patterns and all sorts of problems. So the idea is that you have input X here, and the reconstruction is basically the same X, and you try to learn this Z vector so that it encodes everything that's important about the X in very small vector. Hopefully it's clear. If it's not clear, then please type in the chat the exactly what is not clear. But yeah, so that's the main idea. And maybe the other illustration, if you have better illustrations, you can also share with me. But is something like this. So let me see. So you probably know that there are dimension reduction techniques. So these are like algorithms, methods for reducing the dimensionality of the vectors. So one of the method that is not good is the projection method that we know by doing the dot product. Remember that by doing the dot product, we can like have the input of 32 dimensions and output of just 3 dimensions or 2 dimensions, or what we decide. But there are better methods, for example, principal component analysis, that is selecting the dimensions that holds the most variance and then projecting that on that dimensions. This is like using PCA, but there are also TSNA, and the one was UMAP or something. So there are quite a few methods, but the idea is following. So if we have perfect autoencoder here, and we are able to learn this Z vector, then if we plot this Z vector in some dimensional space, for example, in this case, this looks like 3-dimensional space. So in this 3-dimensional space, all of the samples that are forced, like this sample, and this sample, they all cluster together in one cluster. And we have not told the model that they should cluster in this place, but the model optimizes all of this latent space in a manner that it generally like tries to place items in a cluster, so that would be the least resistance for the model to calculate back the decoder part. And there are some methods to encourage these clusters to be aligned by their similarity, but this method is not encouraging that. But at the same time, it still gives you the clusters and the approximate locations of same class images, basically. And this is quite significant because we never told the model what are those classes. The model learned these classes by itself. So is it clear so far what is the autoencoder and what is the advantage of the autoencoder? So if what I said so far is clear, then type in plus, if not minus. Is it clear so far? Plus, minus. Then I will follow up with some few things and then we'll start coding this stuff. By the way, all of this information we also included in the preparation materials for those of you who read it. So I have 2 pluses, we have 7 people online, I need more pluses to continue. Or maybe you can have question. So if it's not clear, then type in the question. So maybe I will also add explanations, some explanations here. So this is the middle, it could be 32-dimensional Z. And then we display this using, this is a 3-dimensional dim reduction, just for the visualization purposes. No, autoencoder is not really principal component analysis, because autoencoder, so the PCA is the method for displaying this, these embeddings into visual representation that is understandable by human being. Otherwise, if I give you 32-dimensional Z vector, it will be not possible to visualize it so that you can understand it. So that's why we use PCA or TSNA or some other techniques for dimension reduction to 3 dimensions. And only then we can display that. So I'm trying to just give this example so that you have 32 dimensions coming in, right? And then you get, with a dimension reduction algorithm, something that's in 3D just for visualization. This is not part of the model. So I just want to emphasize that we are working with high-dimensional Z vectors. If you want to visualize them, we reduce the dimensions. But if you want to use them for, let's say, re-identification of samples, or using the embedding vectors just to find out which sample is the closest one, we would not do the PCA. How, for example, would you get that picture out of the model? You would not get that picture out of the model. You would get the list of 32-dimensional vectors. Then you would fit this to the PCA, find the principal components, and then project on those components those vectors to see this nice 3D picture. That is why I am trying to explain this part, because I think, like, if without explaining this part, maybe you don't understand why at all you need autoencoders. So the one thing that's missing here from the explanation is that let's say this is our let's say some training data set or inference data set. And now if we get some example that was not inside here, for example, some person just draws manually letter 4, right? The person draws letter 4, and you have this image. Then you encode this to the Z vector, just this part, not the other part. And then you would place that somewhere in this dimension, like the high-dimensional space. And what you expect that this point in this high-dimensional space will be very close to the cluster of 4s, and that way, basically, you just created classifier without any labels. So basically, the other way how you could use this is for, let's say, face identification or Apple Face ID or something like that. So let me find some picture face identification clusters. So there are so this method would be very weak face re-identification method, because there are nothing that enforce the arrangement of the clusters in the high-dimensional latent space. But if there would be some enforcement, it would work better. But still, basically, if this is not a scenario of one-shot learning, it would still give you quite nice clusters. So just let me find it, PCA. So let me see, can I find some example? Okay, I cannot quickly find nice picture of the clustering faces, but basically you can imagine that if you have trained your model with some faces and then you give some new face image, then you can check where it stands in this cluster. The other nice thing that interesting that I'm not sure like if you get it or not is that you can also create, this will be your first generative model, basically, you know, GANs and stuff like that. So if you sample Z vector, so forget this part, if we train the model and then we delete this part and then we just take some kind of average vector of force and then add some noise, we can sample new force like in different styles just by using only this part. So this is quite powerful. You already have the capabilities of array identification and also generation. So this is quite cool. Okay, so we'll move to the classroom. In the classroom, I will open now the task 13.2 with the two tasks that you need to do there. And you should be able already to complete those tasks because they are quite easy. So let me share you this screen. So if I open this one, so there is a classroom task 13.2, and you need to download the template. And you need to, first, what you need to do is to run the template, because otherwise it will be very long before we can start working with it, because I'm chosen the dataset extended MNIST, that is like MNIST but with more images, with more letters and numbers and all sorts of written signs. So if you download that template, and then here I have this template. See, there is a dataset extended NIST, EMNIST. So if I run this one just with the run, I will see that it is downloading the images. So please run this code so that you download this dataset. I stopped it because I already downloaded. So my question will be two parts. So first, let's start with, do you have a template ready to work? Ready to work. 13.2. So this is my first question. Type in plus minus or some question. And if you type in plus, immediately press run, so it starts downloading this dataset, because it might not be too fast. So maybe you will need to wait 5 minutes or so. So please do that, and let me know if your template is ready for work. Meanwhile, I will share some stuff on the Jamboard. So basically, what I'm going to share here is just the same things that is requested to do. So while you are downloading the stuff that you have on the task, like I mean the dataset, while you are downloading the dataset, you can already start implementing the tasks. So one task is really simple. So one task that you need to do is to implement the loss function. So the loss function, for this case, we will use the mean squared error. So you implement the loss function, and you also implement the model, the encoder part. So when you will run it, you will see funny pictures in the decoder part. That is what it is expected. So the funny pictures of the encoder part are expected because we have not yet implemented proper decoder. So let's see. So this is the module that we need to implement. It will be much easier to see if you look at the, like, if you zoom it in. So this is going to be the task 13.2. So you have the loss and the encoder. I will try to improve this image right now. And what else we can do? So yeah, you should start coding that and submit when you have done it ready, because otherwise it will be too slow with this tutorial workshop. So my next question will be, so have eNest downloaded yet? And again, plus minus. So from previous question, I got 5 pluses, so that's good. Almost everybody is ready to work. And then the next question is the downloaded already? While I'm waiting for that question, and while I'm waiting for your code, the image is very low res. Yeah, you say that in the task it is at low res. Let me check. Let me check. So I see that it is not low res if you download it, but let me see. So if I press save as this image, not like that, but there was somewhere button to download it somewhere, then it is a proper size, but I will also improve it. So I will maybe split it in a half. Yeah, on Jamboard it is low res because the Jamboard is small. So I will try to fix it quickly. But meanwhile, you can start working with the image from the Google Classroom. So you should not have serious problems implementing this model. So I will wait for some of you to finish it already. So as I said, don't worry about the output part. So the decoder part, now it's not finished yet. It might look funny and not really beautiful, but that's no problem. So okay, I cannot yet fix it like that. Let me think. I will find a way how to improve the image quality here. I will split it in 2 parts, most likely. So if it's something not clear what to do, then also please ask. Meanwhile, I will prepare the small update for that image. So the update will be very soon. So I'm just a second. I will update this one, and then I will look at your questions. So I prepared a better version. Oh man, what is this? So didn't work like that. Just a second. Okay, like that. Yeah, so the encoder is looking like that. So I just split it in two parts so that it's visible a little bit. Okay, so we have autoencoder here. I see one minus with regards to, so I propose that you already, all of you, start coding those tasks and don't wait for download. So when it's downloaded, then you can run it and test if you don't have bugs. But meanwhile, please start making those tasks. And I will also in like, let's say in 5-10 minutes, let's say 10 minutes, we'll start showing how to do this. And hopefully some of you already will be able to submit this task. No, at this moment, nobody has yet submitted this task. So I will turn out the microphone, so please try to do this. Even if you don't know how to do something and you try, then please submit what you are able to do. So then I understand what are your capabilities and I can help you out. Or if you have questions, then type in the chat. Okay, so the microphone was off, sorry. So here the stride is 1. I think, yeah. And let's see if there is some other place where something is missing. Okay, so I think everywhere where you don't have stride written, it's a stride of 1. So stride of 1 for the first one, again stride of 1. And let's see, do you have any other place? missing, so I think not. So yeah, so just follow up. So in general, like you can even make a little deviances from this task as long as your encoder at the end produce the embedding of 32 dimensions. So here should be the output, should be basically, so this is going to be the output is going to be 32 by 1 by 1 in general. And if you flatten it, then basically the output should be flat embedding would be just 32. So this is what we want. We want this embedding that we can use in that beautiful like space. Actually, like I probably will do in homework the task so that you can create this PCA space or some other dimension reduction method, so you can look at those embeddings. Right now, nobody has yet submitted the task, so I will still wait a little bit. Also, let's do another round of a question. So let's try again. So have eMNIST already downloaded? So this is like the first question. Plus, minus, is it still downloading for you or you already got it? So if you got it, please type in plus. If there's some problem, then please type in what is the problem. So I see some problems here. Let me see. Hopefully the problems will not be related to the dataset. So I have 80% for Kirill. The problem was that I have used mobile data, right? There's some pluses. Then Lee have RL upon loss value, only element terminals can be converted. So the Lee error means that he did not implement correctly the function. So the function is, if you look at the function, it means there is a summation, and then division by the numbers. So that basically this is a mean. This is mean. So if you calculate average mean value of these vectors here, then, or the matrices, then you would have just one value, and then it would work. So if you don't have just one value, that means that this equation is not implemented correctly. So please look carefully at the equation, fix it, and then submit it, or submit it what you have, or like if you don't know how to fix it at all, so you can submit what you have then. So let's look what is here. So what do we have? So the Christopher's is already submitted the task, so that's great. We're waiting. I see that some of other guys are also quite soon ready to submit something. One thing that you will notice that the visuals that we have displaying after every epoch, they are not perfect, because the class names, as I found out, that for extended NIST are a little bit mixed up. We'll need to find the correct class names later. So I will check what the Christopher submitted. Seems great. I like it. I think in general, like if there is no error of what he submitted, then it's basically great. So okay, I see if there is. Yeah, of course, the loss will be completely off, because you understand why it's completely off. Probably Christopher should be able to understand why the loss is completely off right now. So let me look. I will start showing some stuff. I see that some people are struggling with the loss function. That you should not be struggling with it, actually, but it's fine. Like, it's better that you try, not give up, you know. So the error that Lee shared, this is quite normal, you know, like it's expected, because it means that you're trying to select one item from a vector of losses, but basically it will never work like that. Okay. So let's start doing by this second part. So here I will zoom in a little bit. Okay, this is something not really what I was expecting. Unfinished, right? File, save as this as TMP. So just that I have another file here, right? Okay, cool. We have it already Lee submitted. That's great. So I will check that a little bit later, but that's a good progress that you are able to do this now. So now, and I will try to complete these parts. So some people are struggling with the loss. That's really strange, because this is a mean square error. So that means that you recall mean. So that is the part of the equation that's very easy. So then the next part of the equation is the y minus y prime, right? So I have also that Kirilo submitted. That's great. So here we squared it, right? So this is very simple stuff here. We use the very basic mean square error, like the one of the first things that we did. Like we even made the derivatives by hand for that. So here, let's write all of this stuff with the encoder. So convolution, the in channels is 1, out channels is 4. The kernel size, so it should work without errors, if I may say. So if you have errors, then it basically means that there is something wrong with this code. So with your code. So relu, just by just so that it would be more fun, maybe. Oh, no, I will just stick with the task. So torch, and so I will do proper architecture for you at home. So num features 4. So now we have a small block that's kind of repeated, so I can try to just copy that part, like this thing. So now this is repeated again for the next part. So for the next part, this is 4 in channels, of course, 8 out channels, kernel size 4, stride 2, padding. So if I would be not nice, I would ask you to calculate all of this stuff, and also the dimensionality of the embedding at the bottom, so you already know how to do this. But in this case, we already have all of the numbers ready for you. You just need to place them in. So here the next part, the 8. So this one is not changing the channels, it's just working on the width and height. So there the stride is left as oh, by the way, in this one I left out. So the stride by default is 1, and the padding by default is 0. Padding 0. So here the stride will be 1, the padding will be 0, like that. Then the output will be 8. Then the next iteration, so we'll have 16, oh sorry, 8 to 16. Then we'll have the 4 kernel size. Then the stride will be again 2, so we're reducing it by, so we're reducing it twice, but not really exactly, because we have padding of 1, but still fine. So then 16. So it's not really like perfect model, but it will work. So then from the 16, we have again the one layer where we just don't change this size. So 16, 4, stride 1, padding 1, hopefully, dash size, yeah, like that. So, and then I guess the last one will be 6 to 32. 16 to 32. Then 4 to 1, 41. And if this is correct, then by running it, it should not crash. If it's not correct, there's going to be error. So if I run it, okay, it's not crashing. Cool. And here is also the thing that I was talking to you, that the class name here, the B, A, H, so on, so those are wrong. So the classes in the dataset, the labels are somehow mixed up. I will, for the homework, hopefully will find the correct labels for this dataset. I think this is a bug in the Torch Vision. So, but that's a small issue basically. And then you see that the decoder is really dumb, and it just creates some random stuff basically, because we don't have proper decoder yet. So we need to create a proper decoder. This is going to be the next task for creating the proper decoder. So I will briefly open the task in the Jamboard, or I mean in the classroom, but before that I will explain what to do. So if you go, then there's going to be the task 13.3. So task 13.3. So you will need to do 2 things. So first thing regards to decoder, of course, decoder. So with the decoder, it will be, I think, the first time when we start to use the transposed convolutions or some kind of generative model type of things. So the transposed convolutions have also the equation for the output dimensions. So if you remember, there was one equation for the convolutions. Here the D is dilation. So dilation is, in this case, it's always 1. So let me also type in D is dilation. So I will double check if I'm not misspelling this name. Dilation convolution. Oh, sorry, I am misspelling it. Dilation, sorry. So dilation, right? So that is basically just to visually maybe explain so that your let me show. So when dilation is 1, then your kernel looks like this. When dilation is 2, then your kernel will look like this, for example. So it can have some spaces in between. But in this case, we will not use really dilation. Dilation are used in some specific models, but basically I'm just writing it here because it's in the equation, and you should know this name because it appears time to time in some papers and stuff like that. So here the dilation is 1. So this is equation for the transposed convolution. Dilation is 1 for this type of kernel. And the next thing that for the transposed convolutions that will help to understand how they work is the following image. So I think in the Pytorch it is called conv transpose 2D. So I will also write down that one. So the actual name of the function is conv transpose 2D. And what it does, so you have input image here, and you have kernel here with the marked colors, and then you see that it calculates the values with regards to kernel and plays that on the larger image by the method as displayed here. But basically, so it's just using the same value from the 1 pixel and then doing all of those dot products and summation from that 1 pixel to create the larger image. So it's like kind of the opposite direction as the convolution, but yeah, like so you should not actually spend too much time I would say researching all sorts of things with transposed convolutions, because in modern models they actually don't use anymore those. They just upscale and use the convolutions that don't change the width and height size. But still, this is something that is useful to know. And the other part that you will need to implement in this model, so is the denoising. So I mean adding the noise. So that's why actually in your data loader I specifically created 3 types of inputs. There is a X, right? So then you will have the Y here, right? And this is going to be the last one. It's going to be Y prim. So I want you to create first the decoder. I will give you architecture in a moment, and I want also you to create the noisy data set. Basically, you will just add the noise, so noisy input, and this will be called denoising autoencoder. Denoising autoencoder. If you read scientific literature, it says that denoising autoencoders perform much better than simple autoencoders. So you will have this part as well. Okay, so I will add this to the Jamboard to the Google Classroom. Sorry. So I see five submissions of the previous task. That is excellent. Almost everybody that is attending this session is able to do this. This is great. So now you can start working on the next task basically. So this is going to be 13.3, the decoder plus the noisy input. So I will add the architecture. So this, you will use the same template as from the previous task. You don't need to create a new template, right? So you use the previous task template and just complete the decoder part. So I'm dropping it in and adding to the topic of autoencoders. So it should be live now. in the Google Classroom, the task. So I will maybe add a little bit more details. So implement decoder using model schematics, and also implement data set X as noisy using some kind of random under 0.5, then set it as 0 pixel value. I will also copy this one here. So if you have questions, type in the chat. I will just look it in a second. So basically, if the random for the pixel is under 0.5, then set it as 0 pixel, and you will create this kind of noise here. So this is what you need to do, and the actual model that you need to make, I will add that as well. So in the slide 5, let's have the model. So this is the model in slide 5. Decoder. And yeah, so the idea is that the embedding in the middle part, either by Euclidean or by cosine distances, will kind of like have the ability to cluster together by similar images. So, and it's done completely in an unsupervised manner. So we're not telling anything in regards to labels and stuff. So I hope the task is clear. So maybe let's check if the task is clear. So I will ask, is the task understandable? Plus, minus, and if minus, then ask what exactly is not clear. So I typed that question in the chat. Please answer if you can. And basically this kind of decoder model, the model that is made for generative part, is something that you will also see in UNet and some other types of models that I know that, for example, Kirill and Kirill and Christopher's should be able to work with the UNets very soon. So this is a first step towards UNets basically. So I see 1 plus with regards to tasks, so please try to do this task and submit the results. And if you submit results, you will start seeing cool stuff happening. And also you can run this code directly on Google Colab, and then you will see even cooler stuff. But you will need also to find the hyperparameters probably, because the default hyperparameters are never the optimal hyperparameters. I didn't quite understand about the second part, but so the second part, so this is a transposed convolutions. So the transposed convolutions, by the nature, increase the size of the input width and height. What do I mean by hyperparameters? Okay, so width and height. So this is a width and height of the input, and if you see the width and height of the output, depending on the stride and the kernel, is much larger, and you can see that also by this equation. And this is basically kind of similar operation than with the kernel operation that was in the convolution for reducing the size. Now it's just like for increasing the size. So that is one part, and you can implement that using basically you have here where you have these, I hope, yeah, so convolution 2D. So these are all of these are transposed convolutions. So transposed, so it's actually con transpose D. And with regards to the hyperparameters, let me show you, are actually the learning rate, the batch size, and stuff like that. So, and also the depth of the model, for example. There are many hyperparameters in deep learning. So here you have some of the two basic ones, the batch size and the learning rate. So you can never expect your model to work great without exploring and trying to find these, like which works the best. So usually you would do the grid search. You would try, let's say, E minus 3, E minus 4, E minus 5. You would try this one, 32, 16, 8, and so on. And all sorts of combinations. The one thing that there is a correlation, so I can give you that correlation, so that usually the larger the batch size, the larger learning rate, like that. And there is also one big issue. So usually if you have, so another task, so if you have batch norm, you need at least 32 plus samples. So this is a big problem when you have, let's say, large images of inputs. It will not fit in GPU to have 32 images, and this will be a big problem. That's why in the modern models you don't use batch norm, you use group norm, and basically that's the same as layer norm and instance norm. I will briefly touch that by the end of this workshop, and I will also give you to work with that in the homework. So what I'm trying to tell is that the learning rate, batch size, the depth of the model, the loss function even, the optimizer, all of these things are hyperparameters, and you cannot rely with one set and say that this will be the best results. You need to research them. So yeah, I will wait a little bit with regards to the task. So hopefully you're able to finish this task. And meanwhile, I will prepare this last part regarding the normalizations. I see that Kirill must go. I hope that you can catch up with the material later from the YouTube. And others, I hope that you would be able to finish this tutorial. So let's wait for at least one person to submit the decoder part, because I believe this is not difficult. Maybe I will start helping out with the noisy input. If somebody can do this themselves, that is much better. So don't look if you can do it yourself, because that's much more satisfying to basically finish these tasks yourself and maybe have even deviations from the task to make it even better, or somehow like your own way. So that I approve. So I really like that people try to do their own stuff. So here, the one way how you can do this is, let's say, so there is an X. So let me check. Yeah. So here, let's try to have the noise matrix. So NP noise. This is going to be the NP random. So this, as I remember, will be. So let me check what kind of noise it will be. From 0 to 1. I think it will be Gaussian noise, probably, like normal distribution, not the uniform one or some other. So here we can use the shape of, so the shape, what was the parameter there? Size, sorry. The size of this one, of the shape, like that. Then we'll have the NP X noisy, and this we can do with, there is actually many ways how you can do it, but one, so let me think. Yeah, one way could be using the var function. So I prefer not using the some for loops, but you can do for loops if you want. So here under the 0.5 we'll set this as a 0. Otherwise, we'll use the npx here. And now we have the npx noisy ready matrix here. So that's ready. You can use that. That's for the x. That's great. So if I run it and just double check that there's no bugs to see. Create kernel size can't be greater than the actual input size about the last convolution to the Let's double check. Maybe there is some bug. So okay, this worked. So you see that noisy stuff worked. So what about the bug? Or is there a bug or not? Let me check. So the last convolution is kernel 5. The internals. So let's see, kernel 4. The next one is kernel 4. The next one kernel 4. The next one is kernel 7, kernel 4, kernel 5. Okay, maybe I think there efforts you might have some like misalignment with some part of the code, probably. So I mean, like the numbers maybe are missing somewhere. So I will try to do this myself as well and see if I have some problems or not. So basically, the whole structure looks very similar as before. So, but the only change is that there will be the transposed convolution. So convolution transpose. So the input is then 32 to 16, and then the kernel is 4, 1. So I think it's like kind of mirror. So 4 padding 1 stride 2. I think it was kind of mirror stuff. Let's see. Then there is a. Oh, okay. I will just follow this closely. So 32. Then the next one. The next one is from 16 to 16. 16 to 16. Then the 4. So I think it's just a mirror, so you can just copy these parts one by one and change to convolution, transposed convolution, and then it will be fine, I think. So for one, yes, padding only, there is a 0. Okay, maybe I have had a bug before, let me check. No, the padding, no, it is like that. So the padding should be 1. Okay, that's cool. So no, there's no bug. Okay, because it would not work if there would be bug. So here, then the next one is 8. So the 6 to 8, 6 to 8, 6 to 8 again. There's 4, 1, 2. Okay, then the next one will not change again. This is going to be the 8 to 8. The channel size will not change. 8 to 8, then from the 8 to 8 there is kernel size 7. This tried 1 padding 0 only. So let me check if I had that as well up there. Yeah, padding 0, cool. That is correct. So it's quite easily to, you can something like mess up something, but still. So then the next one will be from 8 to 4. 8 to 4, then the kernel, so the kernel size will be 4, padding 1, and the stride 2. So then the features will be 4. That's right, so that's cool. So then the last two things will be the, here will be sigmoid, because the values of the output will always be from 0 to 1. So 4 to 1, the kernel size 5, stride 1, padding 0, like that. First batch norm shouldn't be features, no. So there, okay, yeah, right. Sorry, you're right. Thank you. So I was looking at here the batch norm. So yeah, there should be 16, not 32. So that's of course right. So if I run it, let's see if I don't have bugs. Maybe I have. Anything could happen. So it works. So there's no bugs. So if it don't work for you, that means that you somehow missed some numbers. Something is a little bit messed up. So you see that it is slowly trying to become as those numbers. But of course, there are two things happening here. The one thing that is happening here is that we are running on CPU, right? So see up there is a CPU, and that means that we always only take 200 samples for the just for the coding purposes, so that we can see them. But if we would run this on GPU or the Google Colab, then we will train with everything, and we will slowly to see how these images start to become more like the input images. And at the end, we will get these embeddings perfect. So that is this part. So hopefully some of you can finish this yourselves. Right now I see that already one person submitted. Of course, that's Christopher's. That's great. So let's keep up with the last part of today, because I need also to run very soon. So homework, I will give you the kind of a little bit state-of-the-art type of autoencoder architecture. So the question was with regards to the batch norms. So the batch norms are not the greatest thing to have, but they are necessary, and maybe like the group norms are much better type of way to do this. So I will try to quickly in 5 minutes explain. So you have the X input. So this is in between layers. This is not X of the whole, like the very beginning. So the input, you calculate the mean here, and you calculate the standard deviation, or if it's squared, then it's variance, right? With regards to these means. And then we divide it, so we subtract the mean. So this is basically standard, kind of similar to standardization. But the problem is that one batch doesn't represent the whole data set. That's why we need two learnable parameters, the gamma and beta. So these parameters try to be learned to represent the whole dataset. Then we arrive to another problem, that if we have too small batch sizes, then these values would jump significantly around, right? The variance and standard deviation, and we would not be able to learn these two values properly. So the batch sizes should be big enough, and the reason why we have all of this stuff, remember standardization, so we want to have our data to be nicely aligned. So if we again have, let's say, some kind of like x1 here, one feature x1, and there is a feature x2, we don't want that our features are like lying around all sorts of ways somewhere here, right, in one cluster. We want all of our features to be lying around the 0 here. So basically the batch norm and all sorts of normalization techniques try to push our features towards the middle part so that our nonlinearity function makes sense. Otherwise it doesn't make sense. So so why we make it noisy? So the question about the noisy autoencoder in the chat. So the noisy autoencoder is better than non-noisy autoencoder. You can look up the publications, and also in the reference material that I added to the 13.1, you can read that the research shows that noisy autoencoders are better. They have better embeddings. That's why there is the noisy autoencoder. So anyway, here about the batch norm. So the batch norm is here. So you can see the n. Here are the samples. So this is samples in batch. This is n. The C is channels, and the W is the features. Basically, the feature map sizes doesn't matter. So you see that batch norm goes over the samples of the batch, not the actually. So it's dependent on the batch size. None of the other normalization methods are dependent on the batch size. So I will quickly try to show another example about the normalization methods that you should keep in mind. So hopefully it will work out. Let's see. So if I share my whole screen, and then I will pause that inside the other part. So if we have for example, the input image of R, GB, green, so we have three colors, right? RGB, and okay, this is G, this is B. Okay, it doesn't matter. So we have three input channels, and the width and height, right? So if we select so if we start to train this stuff, and we have, let's say, the batch size 3. So we have 3 sets of these samples. So this means that we have batch size 3, right? Then what we do with the batch norm, so let me also quickly copy this out so I don't miss it. So I will also show another example. So there's going to be some other examples. So the batch norm, we would calculate the mean and standard deviation for every channel across every channel for every channel dimension. So there would be one mean value, there would be second mean value, and then it will be the third mean value, right? So there's going to be the mean 1, mean 2, mean 3, and they are batch size dependent. So that is really bad. Batch size dependency is not what we want. So then they actually came up with the idea to have the batch norm, instead of doing the batch normalization, to do the layer normalization. So the layer normalization would then calculate the mean for every single item in the batch. So there would be, so this is a layer norm. So this would cover all of these items basically all of the maps like in this direction. So and it's not batch size dependent. So for every sample we would just have one large mean value mean. Then there is also another way how to do this using the instance normalization, and that is by even reducing all of this problem even more. So the instance normalization would calculate the mean value for each of these maps separately, like that. But remember that all of these methods also learn the means for whole data set. So I mean, like, it's not something that you would just do as a simple operation, but it will try to estimate what is the mean of each of those maps for all of the dataset samples. So instance normalization, there you'd have the mean for this one, for this one, for this one, and again, this is not batch size dependent. This is good. So all of these other methods are so far good because they are not batch size dependent. And then the third one is group norm that you need to use actually, is something in between the layer norm and the instance norm, where you select only, let's say that some features, for example, let's say you would have some kind of red object on the scene of blue and green valley, you know, like there's a lake and there's a like mountain, right? And then there is a red car, right? So you would have that these two are together and this is separate. So the fun thing is that the neural network models will learn how to split those, but if you just say that we would want to have num2 groups, it would automatically learn to put together those features in one group and other features in another group. So that's why you should use always group norm, and you should do the experiments and find the best value for the number of groups. So this is again new hyperparameter, but this is a good thing because it's not batch size dependent. So yeah, so this is this. So if you have questions with regards to these normalization techniques, then please just write in the WhatsApp group or whatever, and I can help you out with that, but now I need to run. So I will put the homework in the Google Classroom, so it will be hopefully fun. And yeah, so next time we will keep working on the autoencoders, and the time after that we will start working on the units. So that's it for today. I hope it was fun. And yeah, let me know